Hi student, welcome to chemistry class with Emerald, and in today's class we are going to be looking at metallic bonding. This video is brought to you by Igota Virtual Learning, and in this lesson today we are going to be looking at what a metallic bonding is, how a metallic bond is being formed. We are going to look at metal crystal structures. We are going to look at properties of metallic bonding uh, and other key information. So let's get started. Now, metallic bond is a term used to describe collective sharing of a sea of valence electrons between several positively charged metal ions. So the term metallic bond is a chemical bond that results from attraction between metal atoms and the sea of electrons. So if you are asked to define a metal bond or a metallic bond is the chemical bond that results from the attraction between metal atoms and the sea of electrons. This metallic bond we are talking about is responsible for several characteristic properties of metals such as luster, malleability, conductivities, etc. Now, how is a metallic bond formed and how does it form? When the charge is dispersed across a wider distance than the size of a single atom in material, metallic bonds occur. That's how metallic bonds is formed. Metallic bonds are formed when the charge is dispersed across a wider distance than the size of a single atom in material. A metallic bond is formed. Elements like zinc and copper create metallic bonds most frequently on the periodic chart. Metals atoms are firmly packed. Very important information. Metals atoms are very firmly packed in a regular order because they are solid. Metals atoms are firmly packed in a regular order because they are solid. Now let's look at how strong a metallic bond is. Metals have a high attraction force between the atoms. So to overcome it, a lot of energy is required. Don't forget that, like we have said, they are solid and they are very closely packed. And then there is an attraction between the atoms of metals generally. So to be able to overcome this attraction, you will need a lot of force and energy. Therefore, the metallic bond is extremely strong, and of course, this will have effect on the boiling and the melting point. That's why metals usually have high boiling and melting point. Okay, so let's quickly compare uh, uh, metallic, ionic, and covalent bonds. Now, this is an example of how a metallic bond is in terms of the crystal structure. You see that of ionic and then you see that of a covalent. Now, what's the implication of this? Let's look at the difference between ionic and metallic bond. In ionic bonding, for instance, it involves the transfer of electron from the metal, which is the positive here, and the non-metal, which is negative. So it involves transfer of electron between two chemical species. Of course, they arise from difference in electronegativities of the bonded atom. But we are comparing it with metallic bond, for instance. Metallic bonds are formed when a rigid definite lattice of a metal cations share a sea of the localized valence electron. But a very good similarities between them is that both of them involve electrostatic forces of attraction. They require electrostatic force. That means that there is an interaction between a positive and a negative uh, um, substances that generate forces of attraction. So both of them involve electrostatic force of attraction. But a clear difference between them is that one occurs between two chemical species, and of course is based on electronegative difference between them, while the other is formed when there is a sharing of a sea of delocalized valence electron between the lattice of a metal. Now let's look at the difference between the covalent and the metallic bond. The difference between the covalent and the metallic bond. Covalent bonds form when two atoms share electrons in order to fill their outer shell. They share electrons so that they can fill their outer shell. That's what covalent bond does. But however, in metallic bond, um, uh, it occurs when atoms lose their outermost electrons completely. Uh, this, of course, these free floating electrons then bond with other metal atoms to create a metallic solid. Then, of course, a very important difference between them again is that covalent bond occurs with non-metals majorly, while metallic bonds occurs between metals. So these are still a bit difference between uh, metallic bond and ionic bond, then metallic bond and covalent bond. Now let's look at a typical metallic bond, and let's use sodium as a case study. The electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1 with the atomic number 11. Now sodium contains one electron in its valence shell. That means it is univalent. And then in a solid state, metallic sodium features an array of Na plus that are surrounded by a sea of 3s electrons in its metallic features. We'll get to see that one. This is what we're talking about. It contains the it contains Na plus electron that are surrounded by what sea of 3s electrons each. Those you can see the central, the nucleus having the positive and are surrounded by sea of electrons. You can see it there. Now, it would be incorrect to think that metallic sodium as an ion, since the sea of electron is shared by all the sodium cations, so therefore quenching the positive charge. Now we can look at a very key property of the sodium, for instance, so that to understand the bonding and how it affects it. The softness and the low melting point of sodium are usually explained by the relative low number of electrons in the electron sea and the relative small charge of the sodium cation. For example, in magnesium, which contain Mg2 plus, for instance, the electron sea contains twice the number of electrons than the one in sodium. So, due to greater magnitude of charge and electron charge density, the melting point of magnesium, of course, will be higher than that of sodium. So, what are we saying in essence? Is that the valence electron of sodium is 1, that of magnesium is 2. So this will affect the number of electrons C. In magnesium, in sodium, for instance, the electron C here you can see is scanty. So the forces of attraction will be a bit low. So the energy to break it will be low when you compare it with that of magnesium. In magnesium, for instance, the electron C would now be 2 times that of sodium. So you expect the nuclear force of attraction to be higher. So energy to break it will be higher, and that's why magnesium will have higher melting and boiling point than that of sodium. When you compare with it, aluminum with 3 plus, we also have 3 times that of sodium. So those are things that cause metallic bonding, and that's a case study of metallic bonding in sodium. Okay, so let's look at the factors now that affect the strength of a metallic bond, and these factors and determine some of the key properties we see in metals. Now, one of the factors that affect the strength of a metallic bond is the number of delocalized electrons from the metal. The greater the number of delocalized electrons, the stronger the bond. The greater the number of delocalized electrons, the stronger the bond. You have, like we have said the other time, that in plus one metals, for instance, the delocalized electrons are small when you compare with plus 2 metals. In plus 2 metal, the number of delocalized electrons is twice that of plus 1 metals. We are talking about group 1 now. group 1 metals. Then when we got to group 3, especially aluminium, the number of delocalized electrons is 3 times that of group 1 metal. So the more the number of delocalized electron, the greater the bond. Why? Because as the number of delocalized electron will increase, the nuclear force of attraction, or the forces of electrostatic force of attraction between them also increase. This will increase the bond, the strength of the bond, and such it makes it difficult to break, because a lot of energy will be required because of the nuclear energy that has increased. So the more the delocalized electron, the stronger the bond. Secondly, the charge held by the cation, like we have said, if the cation is having +1, +2, +3, as the charge increases, the strength also increases. Why? Because the greater the magnitude of the charge, the stronger the force of attraction between the electron and the cations. The greater the magnitude of the charge, the stronger the force of attraction between the electron C and the cation. So +3 atom or +3 metal have stronger metallic bond than that of +2, and then +2 have stronger metallic bond than that of +1. And that is why in terms of the strength of metallic bond increases across the period from group 1 to 3. Then of course I will decrease down the group as well. So it is very important we take note of this. That's number 2. Number 3, the size of the cation. That now we are talking about the atomic radius. Sometimes question might bring it as atomic radius. So the size of the cation is also important. The smaller the ionic radius, the greater the effective nuclear charge acting on the electron C. The smaller the ionic radius, the greater the effective nuclear charge acting on the electron C. So the electronic configurations of these elements will usually give us an inkling to predict the strength of the metallic bonding, because from the electronic configuration we can know the number of valence electron. We can also determine the charge by that will be on that metal cation. Why? Because if it's having 1 valence electron, we know the charge will be 1, because you will be able to lose that just 1. So it is very important to know that. Now let's look at a question like this. WAEC 2018, the strength of metallic bonds depends on the, what will be your answer? The strength of metallic bond depends on the. So if you have picked the answer, I expect you to have picked C, the number of valence electron. The number of, like you have explained the other time, the number of valence electron. So the greater the number of the valence electron is determined by that's the outermost electron, and of course it will be the charge. The valence electron determines the charge that will be on the metal cation. So the valence electron is the correct answer here. Okay, so let's look at another one. WAEC 2016, what is responsible for metallic bonding? What is responsible for metallic bonding? You have attraction between the localized electron and fixed cations, attraction between positive and negative ion. Then the answer is A, the attraction between the localized electron and fixed positive lattice point, the cations, and we have seen it here. This attraction between the localized electron and the metal ions that is fixed in this lattice will determine the strength of the metallic bond, or the metallic bonding itself. Okay, let's look at the metal crystals. The metal crystal structure. Most metals usually want to have a coordination number of 12, and then because of this coordination number, there are 2 possible regular arrangements for metals generally, and then they are called close packing. So this close packing will give us this densest, because metals have high density. So this close packing will give us the densest possible ways to arrange metal spheres, and then they can be based on both of them are based on hexagonal planes of atom that are stacked. So we can see like this how a typical close packing look like, and this is how metal crystal structure look like. These are a typical close packing. um, there are now two possible close packing that, like we have mentioned. We have the hexagonal close packing, and then the cubic close packing as well. The hexagonal close packing um, usually have a layer of ABAB, um, like we have seen in this diagram here, like this. Or and then of course you can have cubic close packing that has ABC ABC. You can see ABC ABC. You can see like that. So you can have the cubic, you can have the external hexagonal close packing, and these two will give coordination number of 12. That means 6 in planes and 3 in the planes below. So you see there. So we have to take note that not all metals will have a close pack structure. There are usually exceptions. So a few of them will have simple cubic structure. So a few of them will have simple cubic structure. And some other ones could also have body center cubic structure. So these are possible, and those ones have what is called a coordination number of 8. These are possible metal crystal structure. We have the close pack, which is of two types: the hexagonal and of the cubic close pack. And then we have what is called the simple cubic structure. Then we have what we call this body center cubic. So all of these are forms of metal crystal structure. So it is important to learn about this metal crystal structure to give to a metal. Of course, the crystal structure of a metal is usually studied using an X-ray. Please take note of that. The crystal structure of a metal is usually studied using an X-ray. Now let's move to the metallic bonds properties. Some of the properties that now arise when from metallic bonding. You can have in the bond formation, you have electrons that are delocalized among metal lattice, a fixed metal lattice. Then this is just a summary of that property. You have we have metallic bonding occurring between two metals. You have the types of structure that the metallic bonding have. We have electron C. The physical state is solid, melting and boiling point high, no solubility in water, electrical and thermal conductivity is there, and then other properties like malleability, ductility, and metallic cluster are part of this property. This is just a summary. So let's go straight to some of these properties. Now, in the structure of metals generally, there is an electrostatic force of attraction between the positively charged cations and the negatively charged electrons that holds the lattice together. So like we have described, a in the structure of metals when we started in bonding, you have uh, um, you have the positively charged cation, which are these, and they are surrounded by these small balls, these small substances that are called the electron C, and this or negatively charged electron, and these are the two that holds the crystal lattice structure of metals together. Okay, so a metal is therefore seen as, that's the structure now. The metal is therefore seen as a rigid framework of cations immersed in a sea of electrons that serves as a cement holding the three-dimensional cationic network together. So to describe the structure of a metal now, a metal is a rigid framework of cations immersed in electron C or sea of electron, which serve as a cement holding the three-dimensional cationic network together. And this is how it is. This is how it is. This is how it is. Okay, so let's look at other properties that we have been mentioning now. Let's look at the properties we have been mentioning. Number one of the properties of metals that results from this bond is thermal conductivity. The thermal conductivity of a material is a measure of its ability to conduct or transfer heat. When one end of a metallic substance is heated, the kinetic energy of the electron in that area is increased. For instance, if you have a metal plate, a metal spoon, for instance, and you heat one end, or you put it into it, one end of that metal you put into one end, what you have done is that you have increasing the kinetic energy of the electrons in that area. So, and as you increase the kinetic energy of electrons in that area, there is an electron transfer. So this electron will transfer their kinetic energy to other electrons in the sea via collision. So the greater the mobility of electron, the quicker the transfer of kinetic energy. And of course, because of this metallic bond now, the delocalized electron are mobile, and then they will transfer it through metallic substance by colliding with other electrons. So metals are generally, because of this metals are generally good conductors of heat. They are good conductors of heat. Now, this is for electrical conductivity. They are also good conductor of electricity. For electrical conductivity, watch this. For electrical conductivity. Electrical conductivity is a measure of ability to allow a charge to pass through it. Ability of a metal to allow a charge to pass through it. Now, because of the movement of electrons that we have mentioned the other time, the movement of electrons in metal are not restricted. So when you pass electric current through a metal, as illustrated here, when you pass a current through a metal, the delocalized electron, they start moving toward the positive charge. Observe, this is how you pass a potential difference or current through that metal. Then you observe that the electron, they start moving towards the positive charge. From negative, you are moving from negative to positive. They start moving towards the positive charge. Because of this, metals are generally good conductors of it, because the electrons are mobile, they are moving as a result of the introduction of the current. And the more they move, the more mobile they are, the better for them. The more they conduct electricity, because electricity is as a result of electrons, movement of electrons. So the more movement it is, the more they conduct electricity. And that is why it is also important that you observe that when the electrons are more, for instance, when we talk about the electron C that are double or triple in group 2 and group 3, because of this, you observe that most of group 3 metals, especially aluminum, is now used for electrical material, because once the electric current is applied, it has high electron density. They start moving in mass, then they can conduct better and faster. So electrical conductivity is as a result of this movement of mobile electrons. The movement of these electrons when current is being introduced. And we have said that once current is introduced, electrons start to move. They are moving to meet with the positive, from negative to positive. Okay, so that's why they conduct electricity. Another property of metals in relation to this bonding we are talking about is the malleability and ductility. You can observe the a picture here. You see when you apply a force, if it's a metal for instance, when you apply a force, you see the sea of electron, you see the metal cation. At the end of you will see how they align. See the aligning in ionic crystals. That's a salient difference now. In ionic crystals, for instance, when the force is applied, you see negative, positive, negative, positive, negative, and the like. You now see that everybody is there is a strong repulsion, and everybody's there is a way they align. But in metals, they are sliding. Once the force is applied, they are sliding over one another. The positive ion and negative ion are sliding over one another when you compare to that of ionic crystals. So what does this mean? When ionic crystal such as sodium chloride is beaten with hammer, it shatters into many small pieces. And the reason is because the atom in the crystals are held together by a rigid lattice that is not easily deformed. deformed. So when you introduce a force, like from the hammer, in terms of the crystal structure will fracture, and then it will result in shattering of the crystal. But in the case of metal, you observe that we observe from that diagram that the sea of electron enables the deformation of the lattice. So the sea of electron that metal structures have enables the deformation of the lattice. So when they are beaten or fractured, when they are beaten or force is applied on metal, the rigid lattice is deformed but not fractured. So that is why they can be beaten into thin sheet, because the lattice of metals do not fracture easily. So and that is why we say if they are able to be beaten to sheet, they are malleable. If they are able to be beaten to sheet, they are malleable. Now and because they can be beaten to sheet, of course they can also be drawn into wire, and that's why we say they are highly ductile as well. So metals are generally malleable, they can be hammered into sheet and ductile, drawn into wire. You can see like that. They can be drawn into wire. Okay, so um, we said they are malleable and ductile instead of being brittle, as a result of the non-directional nature of the metallic bond. That's an additional point, a supplementary point. Uh, Metals are malleable and ductile because of the non-directional nature of the metallic bond. The ionic bond is directional in the sense that it goes to the in the direction of the force that is applied. But in metallic bond, they have non-directional nature. So the attractive force exerted by the positive ion for the mobile electrons occurs in all directions. So the layers of atom can now move past over one another without disrupting the force between the ions and the negative C of electron. You could see when they apply the force here, um, they are sliding over one another. So it helps them to be drawn into wire and beaten into sheet. Okay, so another property of metals is the melting and boiling point. The melting and boiling point. As a result of powerful metallic bonding, the attractive force between metal is quite strong. So to overcome this force of attraction, energy is required. So that is why uh, metals usually have high melting and boiling point. We have mentioned that. Of course, there are few exceptions like zinc, which is transition metal, cadmium, mercury, and so on. The metallic bond can retain its strength even when the metal is being melt. So generally speaking, high melting and boiling point indicate the strength of metallic bonding. Melting point increase with increase in number of valence electrons to the C, since there is a greater force of attraction between the cations and ion. So as the valence electron increases, the nuclear charge or nuclear attractions increase, and then the more attracted they are, the greater they come together, and then the greater force you will need to separate them or to break those bonds. So increase in valence electron could also increase in nuclear charge and the nuclear attraction, and an increase in nuclear attraction will increase the strength of the bond. So metals have high boiling and melting points. Okay, so another one of their properties is a metallic luster. It talks about the shining appearance of metals. Wow, when light is incident on a metallic surface, the energy of the photon is absorbed by the sea of electrons that constitute the metallic bond. So the absorption of energy excites the electron, increasing their energy level. So these excited electrons, they move. The emission of light due to the excitation of electron attributes to shining metallic luster of metal. So like again, um, uh, metals usually have high densities because their lattices are closely packed. They are closely packed. Okay, so let's look at one question more on uh, which of the following substance contain metallic bond. It's a wire question. Now you have silicon. Silicon is a metalloid, so it do not contain metallic bond. Diamond is a non-metal. Of course, copper is an allotrope of carbon. Is a non-metal. So vanadium, alumina is Al2O3. That's an oxide of aluminium. So it will not literally contain metallic bond. Of course, there is a bit of metallic bond there, but the much more appropriate answer here is vanadium. Vanadium is a transition metal, and they also have metallic bond in them. So this is the answer to that question. Vanadium C is the answer. Vanadium is the answer C. So far we have looked at the properties of metals based on the bonds that they have. We have looked at uh, um, the structure of metals. We have looked at the metal crystal structure. We have looked at uh, the the factors affecting the strength of metallic bonds. We have looked at a case study of metallic bonding in sodium. We have looked at difference between covalent and metallic bond, between ionic and metallic bond. We have looked at how strong a metallic bond is, the property, how metallic bond is being formed, and definition of a metallic bond. So you can take more questions and solve accordingly. Um, Let me encourage you to continue to learn chemistry and ensure you develop more. Bye bye. See you in next video.